The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Problem 5 states a spherical shell has an inner radius r1 and an outer radius r2 and mass m distributed uniformly throughout the shell. The magnitude of the gravitational force exerted on the shell by point mass m, a distance d from the center, outside the inner radius and inside the outer radius is blank. So, now that's a mouthful, so let's just break it down step by step. So we have a spherical shell, which we'll draw like a donut, take the cross section, so you're just looking at the sphere like this, and they tell us it's an inner radius r1 and an outer radius r2. Okay, now it has a mass m, which is going to be distributed uniformly throughout this sphere. So we know it has this mass m. Now it has a point mass of little m at a distance d from the center. Now it says this distance d is outside the inner radius, so outside of r1, greater than r1, and inside the outer radius, r2. So we know d must be greater than r1 and less than r2. So actually, I don't know if you guys can see that or not. You know, d must be inside r2, outside r1. So let's pick an arbitrary point inside this. And that's going to be d, and this is going to be our point mass m. Okay. So when you're doing these problems, if you're finding the force due to gravity, pretty much the best starting spot is going to be this formula right here, which states that the force is equal to a gravitational constant times each of the two masses divided by r squared, where r squared is the distance between the two center of masses. Okay. Now, that distance is going to be d. The center of mass of the spherical shell is this, and the center of mass of the point mass is just where the point mass is located. A point mass doesn't have a radius, it's just considered an infinitely small point of some mass. However, the trick to these problems is that the entire mass of this sphere doesn't contribute to the force. Only the mass inside of the radius where our point mass is located actually contributes. So only this part right there actually does anything. Anything outside of that radius d, any mass out there, doesn't contribute. Hopefully your professor has either derived an equation or explained it at length, but at this point in time, just remember it just has to be inside the radius. If it's outside, it doesn't concern you. So if you're like traveling and you're inside the planet, anything greater than where you're at from the center of the location of the planet, the location of the center of mass of the planet, doesn't actually make a difference to the gravitational force. So basically, in sum up the story, our r has to be equal to d. However, our mass is not going to be equal to m. It's going to be equal to something else. Okay? So way you can figure that out is basically using our density formula is the little trick that you need to remember for these situations. For density is equal to mass over volume. The concept is that the density is going to stay the same no matter what. So just, if you don't quite see it, just follow me in the math. It should make sense to you, and just remember that this is a good approach to doing a problem like this on your tests. So we know that if density is equal to mass over volume, then our mass at any point is equal to density times volume. Now, I actually wanted to change this. What I'm going to do is call this mass inside of d, so mass of the spherical shell with radius of d is going to be, I'm going to designate that as m prime. So in calculating m prime, we're going to actually have to use v prime, or volume of this area right here. So it's going to be the density times, now our volume at this point, we have to remember we're going to use the volume at a radius d, so it's going to be 4/3 pi times d cubed minus the inner part where there is no volume because it's a spherical shell. Okay, so we're going to basically take the volume of the sphere at D and subtract the volume of the sphere at R1. And that'll give us this volume right there where M prime is located, which is the mass that's contributing to the gravitational force on our little m point mass. So we can rewrite this, pull out the 4/3 pi, and just leave our d cubed minus r1 cubed. Now just remember, when you're doing this, d cubed minus r1 cubed it's not the same thing as writing d minus r1 all cubed. Those are not equal to one another. You need to make sure you write it like this. Okay, mathematically speaking, you can't do it like that. So don't ever do this, guy. This is bad. Some people make mistakes doing that. So now that we know what's going on here, we can start plugging some stuff in. So our force is going to be equal to G times this guy, rho times 4/3 pi d cubed minus r1 cubed times our little mass. Remember, this is all our substitution for our m prime right there. This can be divided by, like I said, center mass, and center mass is d. Now, this is a correct answer. However, this is not the correct answer that they want. This answer doesn't match anything on there, so we have to do some manipulation. The only way I can say this is just look at the answers they gave you and see what's going on and try to figure out a way of getting it into the shape of one of these answers. Try manipulating this equation the best you can. I think this problem is they're intentionally trying to be very tricky in the algebra, and I think it's unnecessary, but they're the ones who make the tests, so you have to be able to do what they want. So what we can do to this is you can say F is equal to G. I'm just going to rewrite this out. Actually, rearrange this a little bit. G times rho 4/3 pi cubed minus r1 cubed little m over d cubed. So I didn't change anything, but what we need to do is rearrange this equation. So what we can say, you can always multiply by the number 1. That doesn't change anything. Now, how that helps us here is we can multiply by something over itself when they're equivalent. So what I'm going to do is I'm going to multiply by the total mass of this, but I'm going to write it in 2 different ways. Okay? In the numerator, I'm going to leave it as just mass m, the total mass of it. The reason I'm doing that is because I see in every one of these answers, except for the one that says 0, there is a capital M, the given total mass, in the answer. So we need to get this guy in the numerator. Now, in the denominator, there's going to be your r2 cubed minus r1 cubed, or there's a lot of them have that answer in there. I know one of them doesn't, but we know that's not going to be the right answer because we know this m is going to be different. The answer that says gmm over d squared we know can't be right. It's actually a trick question for those people that don't realize that the mass out here doesn't contribute. So knocking that off, we have to have an r2 cubed minus r1 cubed or something like that in the denominator. So I'm not going to write this mass in the denominator. What I'm going to say is I'm going to use the same exact approach, except in this case, we know our mass, the total mass, is rho times 4/3 pi r2 cubed minus r1 cubed. This is going to be the total mass. This guy, r2 minus r1. Okay, so this is actually equals 1, so we can multiply that through because this is equal to this that I just wrote down there. Now with that, generally on any test, you need to do all your cancellations. So we have a density in the numerator and the denominator. We have a 4/3 in the numerator and the denominator. Pi cancels, and that looks like just about everything. So I'm going to rewrite this out, leaving the g up front. We have our big M, our little m, and we have our minus r1 cubed, all left in the numerator. Okay? Now in the denominator, we're going to have our d cubed. That didn't cancel. Nor did our r2 cubed minus r1 cubed. Now, hopefully you realize that those don't cancel out. So this actually is presented in the form of our right answer, except for the fact that I have been constantly writing d cubed in the numerator. I apologize, I was stuck with the d cubed there. R squared is in the numerator, so just looking at the answers, I noticed that. Don't make that mistake. But this is the answer. It's presented in the right form. Sum everything up. Make sure you remember that the outside of the sphere doesn't count. Make sure you write your formula correctly with the d cubed minus the r1 cubed. Use your density to convert into terms that you know in terms of the radius, and just manipulate the numbers. Remember, you can only multiply by 1, so you can multiply by something that's equivalent to itself over itself. And that's how you solve this problem. It's a tricky question, probably the question that would take the most time to solve for this test.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.